Here's a video guide to Chapter 2, Vectors. It should help to take a look at these chapter notes to help you solve some of these problems. So we started out with a treasure map, and everybody was able to figure out what to do. You were supposed to lay out 3 legs of a journey from some starting location, an origin. Now, normally when we're in school, a lab group will write down the legs of their journey with the starting location and then try to give that to another lab group to see if they can follow those instructions and find the treasure. The whole idea is, can another lab group repeat what you've done and follow your instructions? Well, when you're done, you're supposed to make the treasure map. And we've gone over this plenty, but here's an example if you're not sure what to do. You lay out your legs right here on the map, and then you were supposed to find the one leg that will complete the journey without doing all 3 of those. This is the one leg of the journey that replaces all the others. Now we can solve for this thing mathematically. I think everybody figured out that, yeah, you just go down and over, and you kind of make a triangle where there was none, just like what we did with the flagpole lab. And we were able to figure out how to do that using the Pythagorean theorem and inverse tangent. And you can calculate this angle because you need to have a direction and you need to know how far to go. And then you can measure this. You could use a ruler or another sheet of graph paper as a ruler to measure how many blocks. You're using a scale here. And these numbers should be close to each other. They're certainly not going to be exactly the same because you're measuring on the paper versus calculating, and nothing's perfect. What we did differently in this lab this year is that you were asked to measure this directly on the floor. So that you did this on the floor of your room. So we've got a graphical, a mathematical, and an experimental value. Well, surprise, you've been using vectors. What's that all about? Well, a lot of people don't like all this terminology sometimes, and it seems a little intimidating. So we decided not to tell you that you were using vectors until you were done with that lab. So what is a vector? It's got a magnitude with a direction. That's what a vector is. And you've used them every time you've tried to give somebody directions to get to, say, your house. The vectors that we're using in this lab are displacement vectors. They have a distance as the magnitude. And then, of course, the direction was which way you were going, north, south, east, or west. So it says here, we'll be using vectors all year. Yeah, this is never going to go away. Make sure you're good at this stuff. Let's take a look at an example in 1 dimension. Here we have a displacement of 5 meters and then 3 meters. So what if you walked 5 meters and then you walked 3 meters? Hey, you just add them up. It's 8 meters, and it's all going to the right, or in this example, we're talking east. So what is the difference between distance and displacement? The distance is just how far you've gone. The displacement is that distance with a direction. There's an example right here. Here's more examples of the same thing. So you should be able to go through these examples and test your abilities, cover up the solution, and then try the problem. Now there's something called the equilibrium. Let's go back to the treasure map. You're starting here at the origin, and that's what we call the resultant, the one vector that replaces the others. The equilibrant is the one vector that cancels these other vectors. So if we go down, over, and up, the equilibrant takes you from the finish to the start. The equilibrant has the same magnitude, but the opposite direction. All right, as you can see, here's another example for you to work out, and you can cover this up and try it out. Now, how do we specify the direction of a vector? We went over this in class. I have it on the other video, but if you want to review, here it is. So here's north, south, east, and west. This vector has a direction of 30 degrees north of east. You're going north from east. This is just out of math class, 50 degrees counterclockwise from the positive x-axis. And here in compass bearings, you start at 0 degrees where north is, and you go clockwise. And you can look at the compass on your phone and you can see the degrees laid out just like this, and you just report how far around you are. So in Compass bearings, this is 210 degrees. Well, that would be the same thing as saying 30 degrees clockwise from the negative y-axis, or 30 degrees west of south. Does the order of the vectors matter? If you went over and up, you would have gone 11.2 meters at 26.6 degrees north of west. What if we went up and over? The same vectors up and over. You'd still end up in the same place. If you reverse the order of the vectors, it doesn't matter. Now, there's lots of other vectors we'll be using. We'll be using force vectors, velocity vectors, acceleration vectors. They all have a magnitude and a direction. If I asked you to push on a block with 10 pounds of force, you might ask, which way do I push? So that would turn the force into a vector. Now, velocity has a speed and a direction. So the speed, for example, the speedometer of your car just tells you how fast you're going. It doesn't tell you the direction. So if you wanted to put a direction to that, that would turn it into a velocity. That's discussed right here. Now, not all measurements are vectors. For example, mass, time, density, they're only described with a magnitude. We would call those quantities scalar quantities. Oh, look at this, a problem set. And the answers are in the back of the chapter. Okay, now we're ready to talk about the Orienteering Lab. You downloaded the compass to your phone and you went outside with your meter stick and we found your pace. Tells you all about it right here. You walk 10 meters and you count your pace. Then we had to learn how to use the compass. This is a person being used as a marker. Your line of sight goes from your head looking through the compass at the degree mark that you want to travel on. So if that's north and this is east, then this would be somewhere around maybe 70 degrees. So at 70 degrees compass bearings, we put a person out there, you aim for that person, and then you walk in that direction. Well, when you look at this checklist, you want to have a good lab sheet, follow everything on here. This is an explanation of how to write up the lab in detail. You were supposed to follow 3 vectors. In this case, around your yard, you made them up yourself. If I was in Gike Park, maybe I could use these vectors here. So vector 1, 15 meters, 60 degrees. Let's see what that looks like on my map here. I'm starting over here. I have my compass, north, south, east, and west. I've listed the vectors right here. So the first one is 15 meters, 60 degrees. These are all in compass bearings. So I start at north and I crank over 60 degrees. And now I have to follow my scale. How long do I make this? I could just use another sheet of graph paper, rotate it so that it lines up with this line, and draw out how far to go. So the first vector is 15 meters. When I get to the end of that vector, I put a coordinate system here, and then I draw out the next vector. It says 310 degrees. Again, north, south, east, west. If I go around here, that's 270. Then I have to get to 310. So I have to add another 40 degrees. Then I have to use the sheet of graph paper as a ruler and lay out the number of blocks to get out to here. So if I held my paper diagonally to use as a ruler, that would work out to be about 12.5 blocks. Okay, the last vector, 10 meters at 180. So there's the 180 degrees, and I'm just going to go straight down here, 10 meters. Now, where is the resultant? It's going to go from start to finish. It's the one vector that replaces these others. Well, now, how do I actually do the math to figure this out? People have been asking me, how do you get the math? It would be pretty easy to do it graphically. All you have to do is use the ruler and measure that line, get your protractor out and measure an angle. But the math, yeah, you break everything up into components. You take this vector here and you go over and up. You take this vector here and you go up and over. And this vector just has you going down. It doesn't have any x component. Now, I'm using the term components because we've already talked about that in class, But this lab was designed to be set up so that you could probably figure that out for yourself. Going over and up and then over and then down, you're doing the same thing as you did in the treasure map. You're converting a hard problem at angles into something that's more manageable. So you're going to take the 15 meters and multiply by the cosine of 30 degrees. Hey, you got 12.99. Take 15 meters and multiply by the sine of 30 degrees, and you get 7.5. Well, that's the trigonometry that you're going to be doing, just like we did earlier in the year, for every one of the vectors. Now you get all your components together, and now you have to figure out, how do you get from the start to the finish? You're going to go over 6.14. Well, how did we get that? Well, if you take 12.99 going to the right, and then going to the left is going to be 19.15, you just add them up. And what we mean by add up is you pay attention to the sign. That would be a positive 12.99. This would be a negative 19.15. You add them up and you get negative 6.14. We're going up 7.5, we're going up 16.07, and then we're going down 10. Well, that's going to add up to a total of 13.57 going up. Well, now we can put down all the answers. We have it done mathematically. How? By taking these components and doing the Pythagorean theorem, you can get 14.89 meters. By doing inverse tangent, you get 65.7. You need to add 270 degrees to that to get 336. How do we do it graphically? Measure it with a ruler and a protractor, and it's going to be pretty darn close to your mathematical if you drew the diagram truly to scale. The one that'll probably be off the most will be the experimental. How do you do this experimentally? You have to leave a marker at the finish, walk back to the start, and then get out your compass and measure an angle using your compass, standing behind the compass and looking down the line at the finish. Read whatever the compass says, and then paste this off, and you've gone from the start to the finish. You've got 15.5 meters at 345 degrees. Like I said, it's probably going to be a little bit further off than the graphical and mathematical difference. The mathematical, that should be the best answer. And here we have a summary of how to do all this. You break up the vectors into x and y components, and then it's showing you the math. You add up your x's, you add up your y's, and here's the math showing us how to do that. And then you find the resultant using the Pythagorean theorem. It's all laid out right here if you want to open up these notes and take a look. So here is the 3-step method for adding vectors. This works for any number of vectors. You could have had 50 vectors and it would all be the same. Resolve all vectors into x and y components. Sum the x components, sum the y components. Then use the Pythagorean theorem and tangent to find the resultant. Separate diagrams may help keep things neat. There's no need to do everything on one sheet of paper when you're doing the math. You could, for example, have one diagram for vector 1. You could have another diagram for vector 2. You could have another diagram if you tried to add these together, just so that you could keep things nice and neat. So here's an example. Here's all the math. You can cover this up and test your abilities. Now, can you move the vectors around on a diagram? Once you set up a scale, you're allowed to move these vectors anywhere you want to, but you can't change their direction once you establish what that direction is. Okay, this I'll be showing you is my computer program that adds vectors. Some of these things are available online. I wrote my own program. I'll be showing that to you. We'll play around with that. Now, this section is on placing vectors tip to tail or tail to tail. When we do the displacement vectors in the Orienteering Lab or the treasure map, we did one vector, then the other. This is called placing the vectors tip to tail. The tip of this vector is to the tail of the next one. It helps us see where we're going from start to finish. But there's another way of drawing these vectors, and that's tail to tail. This vector and this vector are having their tails touch. If you were on the deck of a ship that was moved 10 meters east while you walked 4 meters north, those motions happen simultaneously. And sometimes we want to represent that by putting them tail to tail. Where is the resultant for this? The resultant is easy to see here. You're going from start to the finish. But when you have the vectors tail to tail, kids do the silliest things. The resultant is still the same place. It's going right down this way. But what kids do is they start making triangles. They say, oh, we're going to start here and go here, or we're going to go here and go here. They don't even put an arrow on it. Don't do this. It's wrong. You're supposed to start here, and then following tip to tail, it'll bring you up here. Or if you went up and over tip to tail, you'll still get to the same place. So remember now, whether you draw the vectors tail to tail or you draw them tip to tail, you still go from the start to the finish. It's the same resultant. Now, another example of this is with forces. Imagine a friend grabs your arm and pulls you this way. Another friend grabs your arm and pulls you that way. You're certainly not going to go diagonally across from here to here. You're going to go between these vectors somewhere, and that's the resultant. So you can try this with a friend. Okay, I have another computer program we'll play with that helps us practice visualizing all these vectors. And this is a good example for velocity vectors. We'll pull that up. All right, let's take a look at this example. Another one for you to try. A bird is flying 7 meters per second east. And this air, when I say calm air, I just mean it's not moving. That's how fast the bird's flying through the air. Now the wind starts blowing 5 meters per second south. Now, don't you think that bird is going to be thrown off course? The bird is flying 7 meters per second this way, and the wind is blowing this way. These vectors both act on the bird simultaneously, so I'm drawing them tail to tail. If I want to visualize the resultant, I could say 7 meters per second, then 5 meters per second, and that's the resultant motion of the bird. The magnitude of this resultant is known as the ground speed. And then we throw an angle on that, we have a vector. How fast the bird can push through the air is called the airspeed. Okay, now it's the same bird in the last example, but now it needs to reach its nest, which lies due east. That means the bird has to start here and end up going this way. How does the bird end up going east if the wind is blowing south? The bird's going to have to angle up this way, and the bird can head off in this direction, and then we can put this vector tip to tail, and it'll bring us back down to east. So you can see what we've done. We don't know what angle yet to solve for. We don't know what the angle will be yet, but we can lay out the vectors and say the bird can fly 7 meters per second through the air, and then the wind brings it back down to east. And that's where the bird wants to end up going, along this line. Well, that's the resultant. Now, you might find it a little strange that we have a resultant along an axis. There's no rule that says you can't do that. It's just the one vector that replaces the others. And so the resultant this time ends up on an axis. Now, you can solve for this angle using trigonometry. And here's the work to show you how to do that. Well, here's an alternate solution on a diagram. You can take a look at this bird's flight vector and break it up into two components. We can say there's a y component and an x component. If the wind is carrying the bird south, this y component needs to cancel this. So we make that y component 5 meters per second. Well, the only thing left then is this resultant. The only thing left then is this x component. And that is the resultant. Now, how many vectors do you see here? It looks like we've got 1, 2, 3, 4 vectors. No, we only have 2. We have this vector and we have that vector. Now, if we break this vector up into components, we don't look at this one anymore. We only look at the components and the wind. Let's go over how to use a 3-step method for adding vectors. Okay, so here we have an airplane. Here we have an airplane that's going to fly off in an easterly direction, and it's going to maintain an airspeed of 200 miles per hour. And then the wind has a velocity of 40 miles per hour, 60 degrees south of east. Well, we got to find the resultant. What's happening with this plane? A diagram shows us the plane travels this way, the wind is going this way, and that's going to be the resultant. The magnitude of that resultant we call the ground speed. This example tells you just take this vector, break it up into components. So we're traveling 220 miles per hour. We're traveling 220 miles per hour east. The wind is carrying us 34.6 miles per hour south. Well, now we can use the Pythagorean theorem to find the resultant, and then inverse tangent to get the angle. There's all your math. Now, there are some books that tell us about the parallelogram method for adding vectors, and I find it very limiting because it only is going to work with two vectors. You take the first vector, your plane going this way, you take the wind, you bring it over here, and they say make a parallelogram out of it and use the law of sines. Well, look, a lot of kids have suggested that we use the law of sines. Sometimes we need to use the law of cosines, and they only are limited to triangles. If you go back to your orienteering lab, we didn't have a triangle. We had some kind of shape that had more than two vectors adding up to a third. So we have to use the component method. And that is a general method that works for adding up all the vectors. So that's the one we'll focus on. Okay, now let's talk about some notation here, because I really have skipped over a lot about notation stuff. When we write down the variable that represents a vector, we want to distinguish it from the variable that would just represent, say, the magnitude. When you put a magnitude and a direction together, you get a vector. And that notation will be, and that notation would be to take a variable and put a little arrow over the top. That turns the magnitude into a vector notation. Now, this is sometimes an abbreviated form because we don't always can find the arrow on the word processor. We just put a dash over it. The simplest way, though, is to just take the variable and make it bold. And you'll see that in a lot of my examples where I just bold the variable. Okay. Now, let's try this example. Here's a vector A, and here's a vector B. What would it look like if we wrote this as a problem and you had to add them up? Graphically, you would put A and B tip to tail and see that this is A plus B. If I did B plus A, I'd use B first, then A, and I'd still get the same vector. So B plus A is the same as A plus B. So when we say add up vectors, we're talking vector sums. That means you have to pay attention to the direction. You can't just use algebra and add up the magnitudes. That's not going to work. Well, how about vector subtraction? Could I say we're going to take A minus B? Well, if B went from here to here, minus B is going to go the other way. So if I said A plus a minus B, that's the same as saying A minus B. How do we get that? You put your A on the paper, then you do minus B right after the A, tip to tail. You go from start to finish, and you have A minus B. Now we take a look at B, and we try B minus A. We're going to go B What if we wanted to try B plus minus A? Well, minus A is the opposite of A, which was going this way. So that's why we draw it this way. Now, if I start with B, I'm going to say B is going this way. And then I should have had minus A drawn after that. Well, I reversed the order in this diagram, and it doesn't matter. If you go B minus A, that means you're going from start to finish. If we said minus A plus B, you still end up with the same vector. Now, it's in a different location. It doesn't matter. The location on the paper doesn't matter. As long as the same magnitude and the same direction, it's the same vector. Oh, another problem set. So this is what you can do to practice. Look at all those problems to try. Look at them all. And you've got answers here for problem set 1 and problem set 2. And in the packet that you have, I put in the last couple of pages, which has the details on how to do the flagpole lab, including how to find the shadow going up the wall of the school. So please use these packets. I wrote them for you. It's not like you're left lost hanging. You don't know what to do. You can always look stuff up in these packets. Thank you very much.